Have you ever looked up at the night sky and wondered what's out there, beyond what our eyes can see? For decades, the Hubble Space Telescope gave us breathtaking glimpses. But now, we have a new eye on the universe, one that can see further back in time and with more clarity than ever before. This is the story of the James Webb Space Telescope, or JWST, an engineering marvel designed to unravel the deepest mysteries of the cosmos. So, how exactly does this incredible machine work? Let's break it down. First, let's talk about why Webb looks so different from Hubble. Hubble primarily sees invisible and ultraviolet light, the same kind of light our eyes detect. Webb, on the other hand, is an infrared telescope. Why infrared? Well, for two big reasons. The first is something called redshift. The universe has been expanding ever since the Big Bang. As the universe expands, the light from the very first stars and galaxies gets stretched out as it travels across billions of light years to reach us. This stretching process shifts the light from visible or ultraviolet into the infrared part of the spectrum. So, to see the universe's baby pictures, we need infrared eyes. The second reason is that infrared light can pierce through cosmic dust. Huge clouds of dust and gas are like cosmic nurseries where new stars and planets are born. Visible light gets blocked by this dust, but infrared light can pass right through, giving us an unprecedented view of star and planet formation. To see these faint infrared signals, Webb has to be incredibly cold. If it were warm, its own heat would emit infrared radiation, creating a kind of glare that would blind its sensitive instruments. It's like trying to take a picture of a candle in broad daylight. The telescope needs to be cooled to a mind-bogglingly cold -233 degrees Celsius, or -388 degrees Fahrenheit. That's colder than any natural temperature on Earth. To achieve this, Webb has a gigantic sunshield, about the size of a tennis court. This sunshield has 5 layers, each as thin as a human hair. These layers are made of a special material called capton, coated with aluminum and silicon. The layers work like a super effective thermos, with the vacuum of space between each layer acting as a perfect insulator. The side facing the sun can get as hot as 110 degrees Celsius, hot enough to boil water, while the side with the telescope stays colder than liquid nitrogen. It's this incredible temperature difference that allows Webb's instruments to function. Now, let's look at that stunning golden mirror. It's not just one single piece of glass. It's actually made of 18 hexagonal segments that fit together to form a massive primary mirror over 6.5 meters, or 21 feet, in diameter. That's nearly 3 times wider than Hubble's mirror. The larger the mirror, the more light it can collect, and the fainter and more distant the objects it can see. Each of these 18 segments is made of beryllium, a metal that is both incredibly lightweight and strong, and it holds its shape extremely well at cryogenic temperatures. The segments are then coated with a microscopically thin layer of pure gold. Why gold? Because it's exceptionally good at reflecting infrared light. We're talking about a layer so thin that if you stretched out all the gold on the mirror, it would be less than a golf ball's worth. These 18 segments had to be folded up like origami to fit inside the rocket that launched it into space. Once in orbit, engineers on Earth undertook a painstaking, months-long process to unfold the mirror and perfectly align each segment to a precision of 1/10,000th the width of a human hair. This allows the 18 small mirrors to act as one single, giant, perfectly focused mirror. So, the sunshield keeps it cold, and the mirror collects the light. What happens next? The light gathered by the primary mirror is directed to a smaller secondary mirror, which then bounces it into the heart of the telescope, the instrument suite. Webb has 4 main scientific instruments, each with a specific job. There's the near-infrared camera, or an ArcCam. This is Webb's primary imager, responsible for taking those jaw-dropping pictures we've all seen. It detects light from the earliest stars and galaxies as they were forming. Next is the near-infrared spectrograph, or NR-SPEC. Instead of taking a picture, a spectrograph splits light into its different colors, or wavelengths, creating a sort of rainbow. By analyzing this spectrum, scientists can figure out what an object is made of, how hot it is, how dense it is, and how fast it's moving. It's like a chemical fingerprint for stars and galaxies. Then we have the mid-infrared instrument, or MIRI. This instrument sees in longer infrared wavelengths. This is where MIRI shines, because it needs to be even colder than the rest of the telescope, just a few degrees above absolute zero. To achieve this, MIRI has its own special cryocular, basically a high-tech space refrigerator. MIRI is perfect for looking through that thick cosmic dust, to see newborn stars, and even for studying distant galaxies and objects within our own solar system, like comets and asteroids. Finally, there's the Fine Guidance Sensor, a near-infrared imager, and slitless spectrograph, or FGS NIRIS. The Fine Guidance Sensor is like the telescope's navigator, locking onto guide stars to ensure Webb stays pointed with incredible stability and precision. NIRIS contributes to discovering and characterizing exoplanets, planets orbiting other stars. It can analyze the starlight that passes through an exoplanet's atmosphere, helping scientists determine what that atmosphere is made of and whether it might contain signs of life, like water or methane. One final piece of the puzzle is where Webb is located. Unlike Hubble, which orbits the Earth, Webb is much, much farther away. It orbits the Sun at a special spot called the Second Lagrange Point, or L2, about 1.5 million kilometers, or 1 million miles, from Earth. At this point, the gravitational pull of the Sun and the Earth balance out, allowing the telescope to hover and stay in line with the Earth as it goes around the Sun. This location is crucial. It keeps the Sun, Earth, and Moon all on one side of the sun shield, ensuring the telescope and its instruments are always in shadow and always cold. From its giant golden eye to its revolutionary sun shield and its suite of super-sensitive instruments, the James Webb Space Telescope is more than just a telescope. It's a time machine. It's allowing us to piece together the 13.8 billion-year story of our universe. From the first flickers of light after the Big Bang to the formation of solar systems and the search for life beyond Earth. Every image it sends back is not just a pretty picture, it's a piece of a grand cosmic puzzle. The discoveries have only just begun, and the universe Webb is revealing is more wondrous and mysterious than we ever could have imagined. What questions will it answer next? We can only wait and watch in awe. Thanks for joining me on this deep dive into the James Webb Space Telescope. If you enjoyed this journey into space technology, don't forget to like, subscribe, and hit that notification bell so you don't miss our next adventure into the cosmos. See you next time.